Alright, so for everyone in our chem class, instead of me explaining it to several people the night before the lab is due, I thought I would make a video. I thought it would save me some time and you guys a lot of time to do these calculations. So, bear with me here for the limited tech abilities, no camera really or anything. I'm just going to be writing on this whiteboard here. So, in order to do these calculations, this is basically the buffer stuff that we should know, but nobody actually does because it's very difficult. We're going to be using this basic equation right here. The pH is equal to the negative log of H+. We know that already, but we don't know the concentration of H+ after equilibrium and buffering has occurred. So, we are going to find H+ by using the Ka times the concentration of the acid over its conjugate base, which we know is the acetic acid. So, I'm going to do the second step on the data lab calculations. So, the problem is going to be, so I hope you guys have the equation written down. I'm erasing it. If not, you can rewind. After we add 0.2 molar of 1.0 milliliters of HCl to a solution that's 0.1 molar of 50 milliliters of the HC2H3O2. That's the problem. This is the second part on the lab, which is right here. Okay? To do this, we have to convert both things to moles, as we do in every buffer equation, or every buffer problem. We have to use stoichiometry instead of the typical stuff we've already learned with the stoichiometry, or not stoichiometry, the stuff with ice charts. We can use ice charts for that, but this is my ice chart calculations for 2 of the 40 trials we have to do, and it's already a page. This is a very easy technique that Miss Bly didn't actually teach us. But that's okay, because we're going to do that right now. So, we convert these both to, let me get my calculator. Convert these both to moles. We know that the 0.2 molarity times 0.001, because we have to convert it to liters. So we know we have 2.0 times 10 to the negative 4th moles of the HCl. And that is going to be added because when we add these two things together in our equation, which you should have already written, if not, I'll write that next. When we add these two things together, those two together are going to give us and yield our product. And then that is going to buffer, and we find that. So that's what we're going to be looking for. So we convert those two things, the 0.1 times 0.050. Or the 0.1. I messed up here on the calculator. So now we have 0.0050 moles of the C2H3O2. So this is what we are given, basically. Okay? If I'm going too fast, don't forget you can pause the video. I'm just showing this real quick. Okay. So I'm going to erase all that. Now, we are going to write the equation. So, we know that the concentration of HA from the equation I showed you earlier is actually the CH3COOH or the HC2H3O2. They're the same thing, they're just written differently. And we know its conjugate base is CH3COO minus or the C2H3O2 minus, which is the acetic acid. Okay? Or the acetic acid's conjugate base. So, we write our normal equation. We're basically adding HCl to the solution, so it's going to be HC2H3O2. I have it somewhere. Or actually, instead we're going to be using the conjugate, because that is the equation, plus the HCl yields at equilibrium CH3COOH. And then plus the Cl minus ion. So our net ionic is going to be the C2H3O2 minus plus the H plus ion at equilibrium yields CH3COOH. Use that equation to help you. Okay, so using the moles we calculated earlier, we are going to add those two moles together. So in your calculator, the following calculations: 0.1 times the 0.05 plus, so that's the moles of the solution in our beaker when we did the actual experiment. That's what we had in the beaker, the solution that was pre-prepared. We're going to add that to the HCl that we are physically adding, which is 0.2 times 0.001. And that gives us 0.0052 moles of everything in the solution. Okay? And we are going to divide that by 0.051 liters. Now, why are we doing this? Why are we doing this? Moles over liters. What does that equal? That is going to give us the molarity. That's going to give us the molarity of what exactly? Of the CH3O, or the CH3COO H. That is what it's going to give us. Okay. So do that calculation in your calculator, and then you get 0.102. Please don't round. Use the really long, like 10-digit calculation in your calculator, so that way your pH is more accurate. I'm just going to write it on the whiteboard for the purposes of saving time. Okay, so then that is the concentration of HA in our formula. So the formula we're going to be using, again, is going to be negative log of the Ka times Ha over A minus. We're given the Ka. We're given the Ka as 1.8 times 10 to the negative fifth, and that's going to be multiplied by the 0.102 divided by what we just found over the concentration of the conjugate base. Now, we already know that, okay? Now pay attention. I'm not going to be writing this down, I'm just saying it out loud. So, you know the concentration of that is what's already in the beaker plus all of the liters that's already in there. So we just have to change the volume slightly in the calculation for molarity in order to calculate new molarity. So we know that the molarity of the CH3COO minus is going to be the 0.1 times the 0.050. Okay. And now we're just going to be dividing that. Nope. See, even I get confused while doing this. Give me a second here. Okay, I remembered. Sorry about that. Okay, so what you have in solution already is the original solution is going to be the 0.1 times the 0.05. That's going to give you the moles of what is in the solution, which is the CH3COO minus ion. And you're going to subtract now what we used, which was the concentration of the H plus ion, which happens to be the moles, which we calculated earlier, which is 2.0 times 10 to the negative fourth. And that's going to give you the 0.0048 moles. Now that is now not in 0.05 liters. That's now in 0.051 liters because we added that 1 milliliter of the acid. Don't forget that. So it's going to be divided by 0.051. and that is the concentration of A minus is what we needed, okay? So we're going to write that on the whiteboard, 0.094. Okay. So this is the calculation you should have set up for every 40 of these individual pH calculations. No ice charts, somewhat straightforward, but once you get it, it really goes quick. So once you do that calculation, you should get an answer of approximately 4.71 as your pH value. When you do these calculations, they should mirror the results that you got or be pretty darn close if you calculated your pH probe correctly. They should decrease for the first trial. For the second trial, they should increase. For the bottom half, part 2, first trial, they should decrease again. And the second trial, they should increase. So thanks for watching, guys. I really hope that helps. Thanks.